Welcome to a new episode of Chemia, a Chemistry 101. In this episode we will be reviewing a galvanic cell, which is a redox reaction at a distance. And I will explain what I mean by that in a minute. We will be looking at a redox reaction where zinc atoms are oxidized and it will donate its electrons. And it will donate its electrons to copper 2+ ions, which will accept these electrons, and it will be reduced to copper atoms. If we can try to make this work at a distance where we connect the two reagents with a wire, the electrons have to move through the wire, and then we have created an electrical current, which is what we're going to try to achieve. Let's have a look. Here we have two beakers. In the left beaker there is a zinc electrode, which is essentially a zinc rod, and it's connected through a copper wire to the left hand side, where a copper electrode is in a solution of copper sulfate, and the yellow dots represent the sulfate ions. And what will happen is that the zinc will be oxidized and it will donate its electrons. These electrons are needed on the right hand side. What will happen is that the zinc 2+ ions will go into solution, and the electrons will go through the copper wire, to the right hand side, to where the copper ions in solution will accept these electrons. So copper 2+ will be reduced, accepts the electrons, and the ions will move out of solution and react at the copper electrode. This way we have created a current of electrons through the wire, and that's what we are after. However, this is not going to work, because let's have a look at the left hand side. There will be more zinc ions coming into solution, which makes this solution positively charged. And the electrons are negatively charged, and as you probably know, positive charge and negative charge attract each other, so the electrons cannot depart from this electrode. They will be held here by the positive solution. On the right hand side, something similar occurs. The copper ions go out of solution, and the negatively charged sulfate ions remain in the solution. So this solution will become negatively charged by the sulfate ions, and the negatively charged electrons cannot move to a negatively charged solution. So we have to try to balance the electrical charges in the beakers. In comes a salt bridge. A salt bridge is an inverted U-tube with a solution with an inert salt, a salt that will not react with the ions in the solution. And what will happen on the left hand side is that because this solution becomes positively charged by the zinc ions, the nitrate ions from the salt bridge will go into solution, balancing this positive charge of the zinc ions. At the same time, zinc ions can also move into the salt bridge. And this way we can balance the charges in the left beaker, and the electrons can depart. On the right hand side, the copper ions go out of solution, and the negatively charged sulfate ions remain, which we have to balance, and the sodium ions from the salt bridge will balance the negative charge of the sulfate ions. At the same time, the excess of sulfate ions can also move into the salt bridge. This way we have balanced the charges in the electrodes, and we will have created a electrical cell, a galvanic cell, and we have created a electrical current. And this is how in essence all batteries work. When you think about it, after a while the zinc electrode will become smaller, because the zinc atoms are going into solution as zinc ions, and this electrode will be eroded. On the right hand side, the copper ions will be added to the electrode, so this electrode will thicken. And you don't even need a copper rod as electrode. You can even use for example, graphite electrode, which is black, made of carbon, and after a while you will start to notice a brown layer added to the black graphite electrode. If you want to know the potential that a galvanic cell can produce, you will have to find the standard electrode potentials. You can find them in tables, and for copper 2 plus ions, this value is plus 0.34 volts. For zinc, this value is minus 0.76 volts. And to get the potential for the cell, you have to subtract these two values. Beware, minus 0.76 minus, dus 2 times minus, so you will have to add them, and you will get plus 1.10 volts. Beware, you used standard electrode potentials to calculate these, which are measured at standard values of temperature, of pressure, and of concentrations of ions in solution. So if those values deviate, also this potential can differ a bit. Okay, I hope this was useful. I thank you for watching, and I hope to see you at the next episode of Chemistry 101 by Chemia.